this? Good morning.
Good morning.
Wow. Okay. So last day, let's do a little recap, I guess, here. Hey, I want this. Okay, well, whatever. I'll do the review after this slide. How's that? Wow. A bit of review. What did we do last week? We did conditional probabilities, right? And so we introduced conditional probabilities, which means that the probability of something happening is affected by some other thing having happened or not happened before, right? And so that's what makes these probabilities conditional. So from our formula sheet, I know I'm a one-trick pony, but this is what you'll have. This will be your lifeline in the tests. So you want to be really familiar and comfortable with the formula sheet, right? And so that's why I keep bringing you back here, right? For conditional probability, we were working with this formula here, right? And we said, okay, the probability of A given B, right, given that B has happened, is going to be the probability of A and B happening together over just the overall probability of B. And we saw we could use contingency tables to figure out these probabilities if we have the contingency table, but sometimes a tree diagram helps, right? And so to solve probability or conditional probability problems, we use a tree diagram. And the example that we worked on last day was kind of a downer one, the cancer one, right? And so we said, okay, there are two possibilities, right? And so at each set of branches, you want to have all the possible things that could happen, right? And so someone can either have cancer or not. What did I guess I used the complement of C, right? So not C. And then if we do, I think this one was breast cancer specific. And so if we do a mammogram, then of course you could get a positive test result or a negative test result, right? And one of those would be accurate and one of those would be inaccurate, right? But those are the two possible outcomes. And same thing, if you don't have cancer, you could still get a positive result. And then the alternative is you could get a negative result, right? Each with some probability, right? And what we saw was that the probabilities down here, the probability of testing positive, knowing that this person has cancer, right, is going to be different from the probability of testing positive if they don't have cancer, right? Should be lower probably. And so at the end of each of these branches, technically we have conditional probabilities, but usually how we end up writing them is just as a probability, right? And so then if I go down the branch and I multiply down the branch, below here I have the probability of just having cancer and the probability of not having cancer. So some general population probability, right? And so then at the end of each branch, I have cancer and positive, right? And so now I have these combinations. And so at the end of each of these, I get cancer and positive, cancer and negative. Not cancer and positive, not cancer and negative. You multiply down each of these branches, right? You get that and probability, right? And so here, if we multiply down a branch, hopefully you have kind of caught the probabilities down a branch, right? We get the probability of A and B, right? Just generically, if this is A and this is B, right? Or in this example, the probability of C and positive, for example, right? We multiply down a branch. Maybe I'll remove the A and B and just do this instead. So at the end of each branch, you have these kind of combined probabilities of all these outcomes. And one of the things that we said is going to be really useful to check your work is that these probabilities should add to 1, right? This is all the possible combinations of outcomes that we could have, right? And so then we could find things like, what's the probability of testing positive, right? There are 2 ways to test positive. Let's use purple here. So here I test positive, but also here I test positive, right? And so the probability of a positive test is the probability of having cancer and testing positive. Or, right, whenever you're saying or, you're going to be adding these probabilities, right? Or the probability of not cancer and testing positive, right? And so here, if you say or, results in addition. Now I'm going to adjust this slide here. Success. Any questions before we start our application activity, which is just another example? So I left you with this one for Wednesday, and here we are on Wednesday. Oh my gosh. And so it's another kind of health model, but that's pretty common for these types of questions. And so a common epidemiological model for the spread of diseases is the SIR model, where the population is partitioned into 3 groups. Okay, so you can either be susceptible, infected, or recovered, right? You're going to be one of these 3, right? And those are all your options. This is a reasonable model for diseases like chickenpox, where a single infection usually provides immunity to subsequent infections, right? Once you've had chickenpox, it's very unlikely that you'll get it again, right? And so the problem, sometimes these diseases can also be difficult to detect, which is going to affect our probabilities. And so imagine a population in the midst of an epidemic where 60% of the population is considered susceptible. So there's some probability that a randomly selected individual is susceptible, which is 60% or 0.6. 10% is infected and 30% is recovered. So now we've kind of partitioned our entire population into these 3 categories, right? And so that's going to be our first set of branches, is whether you're susceptible, infected, or recovered. So the thing with the tree diagram, and it is on the next slide, so if you work through it, you're able to check your work. But I like to do my trees kind of going down like this. More of a root, I guess. So my first level, it's got really dark in here. Sun clouds over. Is going to be whether this individual is susceptible, infected, or recovered. And we're given the probabilities of these things happening. If you read on, you can confirm that this is going to be the first kind of layer of your tree diagram, okay? Because then we are going to run a test. So the only test for the disease is accurate 95% of the time for susceptible individuals. And so now, conditional on someone being susceptible, then it's going to be accurate, which we need to think about. What does it mean to be accurate if you are susceptible? Accurate would mean what? A negative test, right? A negative result. Because you're susceptible, you don't have it yet, right? And you're not, yeah, you're just susceptible. Yeah? And so then accurate means a negative result, yeah? But it depends on which group you're in, right? The accuracy of the results. And so that's what tells me, okay, well, because it's conditional on whether I'm susceptible, infected, or recovered, then that makes it my second set of branches. Okay. It can also be something like event, the first event, and then the second event, right? And so obviously the second event follows the first event. So then the first event is the first set of branches, and then the second event is the next set of branches. Okay, so we are given these probabilities, and we have 60% are susceptible, 10% are infected, and 30% are recovered. What's one of the things that we can check? Right, these probabilities all have to add to 1, right? Because it has to take into account all the possible outcomes. Otherwise, it's incomplete. Bless you. So now, okay, let me just move this. It's kind of off center. Anyways. So if we have a test, the result is either positive or negative, right? And so now I only have 2 outcomes at the end of each of these branches, right? And that's okay. They don't have to have the same number of branches at each layer. It depends on what the possible outcomes are, right? And so I think I made it too tight. Oh, well. Right? And so at the end of each branch here, you either get a positive result or a negative result for each of these situations. The probabilities, right? If it's accurate, right? We said for the susceptible group, accurate means a negative result, right? And so then the probability of testing negative is 0.95. Whereas for the next one, 99% of infected individuals. And so now if you're infected, an accurate result is a positive result, right? Which is a switcheroo, right? So now here, 0.99 and 65% accurate for recovered individuals. Now, if you're recovered, right, then the result should be negative, right, if it's accurate. Yeah. And so that's a low probability, probably because you have antibodies and things like that going on, and it's hard to detect. So that's tricky. But how do we find these missing probabilities? Right? Each cluster of branches has to add to 1, right? If you are susceptible, then these are my only 2 possible outcomes. And so these probabilities have to add to 1, which makes this 0.05. And then same thing, if you're infected, positive or negative outcomes, those are my only 2 options, 0.01. And 0.65 is 0.35? Question mark? This is happening. Yeah. Math. Okay. But wait, there's more. What do I want to see at the end of each branch? So here, this is pretty sloppy notation, right? I'm not using probability notation or anything like that. And that's okay. You're allowed to do this because it's just to map out all the information that you've been given, right? So as long as it makes sense to you. Otherwise, if you wanted to, I'll erase this, but you could say the probability, of a positive result given being susceptible is this. That's technically true, but kind of a waste of brain space, I think. Right? So I'll erase this. Hey, erase it. There. I want you to show the probability of being at the end of each branch, right? The probabilities of all these different combinations, but all those different combinations should encompass all my possible outcomes, right? And so they should add to 1, right? Unless you've rounded, right? You want to keep track of, okay, if I've rounded, then I need to be a little bit flexible on the adding to 1, right? But as much as you can, you don't want to round any of your values. So now I like to just kind of tell myself what the combination is at the bottom, right? So S plus means S and plus, right? S minus, I plus, I minus, R plus, and R minus. And then below each of these, I'm going to calculate my probabilities. Thanks. You ready? 0.6 times 0.05 is 0.03. 0.6 times 0.95 is 0.57. 0.1 times 0.99, hopefully I didn't, if I did something weird, stop me. 0.1 times 0.01 is 0.000, wait, 1, 2, 3, 1, 2, 3, scientific notation. 0.3 times 0.35, 0.105, and then 0.3 times 0.65, 0.195. Resist the urge to do any rounding, right? Because now I can make sure that these all add to 1. 0.03 plus 0.57 plus 0.099 plus 0.001 plus 0.105 plus 0.195. Whew! They add to 1. Great. So now I'm feeling confident in my calculations. So now we can use this tree diagram, right? And on the test, I'm going to make you do a tree diagram, and most of your marks will be from this work, right? So besides, you don't have to show that it adds to 1, right? That would be kind of an extra step, but that's for you to check your work and make sure that you're on the right track. But besides that, I want to see all of this work, right? Then you can use it to find probabilities. Here, draw a probability tree to reflect the information given above. Right? That would be part A. Probably, I don't know, 4 marks. right? If the individual has tested positive, what's the probability that they're actually infected? Probably 2 marks. I'll show you why. Well, I usually default to 2 marks. So, how do we translate this into a probability question with probability notation, right? And so here we're told that if the individual has tested positive, so given this individual has tested positive, then what's the probability that they're actually infected, right? And so if we translate this, right, this would be given a positive test, what is the probability of I? Which we would translate into a conditional probability statement, right? I want to know what's the probability of I given a positive test. And from your formula sheet, right, you know that it's going to be the probability of I and infected divided by the probability of being, or sorry, the probability, I and infected, I and positive over the total probability of just testing positive. Yeah? And so this is going to look like this, the probability of I and positive divided by the probability of positive, right? And that's mapping from your formula sheet. On your formula sheet, you have the probability of A given B is the probability of A and B divided by the probability of B. Right? Wherever you see an A, you're going to write I, and wherever you see a B, you're going to write a plus. Okay. Here, this is going to be the sticking point, because I've tested positive at the end of this branch, or at the end of this branch, or at the end of this branch. So there are 3 ways that I could test positive. Right? And so if we just kind of highlight these positive tests, right, we see that there are 3 ways to test positive. So from the tree, we see there are, I'll put it up here. We see there are 3 ways to test positive, which means that the probability of a positive test is the probability of susceptible and positive, or the probability of infected and positive, or the probability of recovered and positive. You have these probabilities already in your tree diagram, so that means that you don't have to show the work, right? As long as you've shown me these probabilities at the end here, right, then I'm satisfied. So that's going to be 0.03 plus 0.099 plus 0.105. Let me just confirm that. 0.03, 0.0, wish I could have it on the same screen. 0.099, 0.105. Can add these up. 0.03 plus 0.099 plus 0.105 huge. 0.234. Bet you didn't think there were cute numbers. That's cute though. 2, 3, 4. Now, I have this denominator, right? It required a little bit of work, right, to get there. But now, I and positive, that's this probability here, right? Gets kind of confusing because we use this this probability twice, but because we're adding it in the denominator, it doesn't, they don't cancel out or anything, right? And so it's okay. But now we're ready to find the probability of I given a positive test is the probability of I and positive divided by the probability of a positive test, which is 0.099 divided by 0.234. Which is roughly 0.4230769231. Because it keeps going. I just don't see any more digits on my calculator. So knowing that someone is tested positive, then the probability that they're infected is only 42.3%. Good. Any questions about that one? Yeah.
When we're taking the denominator percentages, I'm just trying to wrap my brain around why we're taking it from the very bottom branches and not the middle branches.
Because you want to have this guy here, right? Mm-hmm. So the probability of a positive test result, this is going to be the probability of S and positive. I just dropped the and, right? And so, but that's at the end of each branch, right? So you have to multiply down the branches to get the S and positive. And that's because these branches here, this probability is the probability of positive given S. So this is the probability of a positive result given S. So knowing that they're susceptible. So it's only kind of halfway there. But if you multiply that by the probability of S, you get the probability of positive, or S and positive, let's say. There.
Yeah. Also, will you explain like why it is accurate, sometimes it's negative, sometimes it's positive?
Yeah, so that one you kind of have to take a step back for, right? And so if I tell you that that I don't have the chickenpox, right? Then if I told you, but I got a positive test result, you would say, oh, that's weird, because that must be wrong, right? And so, yeah, you kind of have to remove yourself, because you want to try to memorize, oh, accurate means this, but if you kind of take a step back, then you'll be like, okay, so if I don't have it, if I'm just susceptible, it means I don't have it. I for sure don't have it. So, well, okay, we know I don't have it, right? And so then a positive result would be inaccurate, but a negative result would be accurate. Whereas if you're here, okay, you're infected, you have it, then you're expecting your test result to be positive, right? You'd be surprised if it was negative, but you understand that it can happen, right? False positives, right, are kind of common. False negatives are a problem too, but we're more kind of in tune with the false positives, right? And so here, right, if you've recovered, no, I had it weeks ago, I don't have it anymore, I know that, then you can still get a positive test result with kind of a high probability, right? Because you've got these kind of antibodies floating around making a mess, but you should be testing negative, right? Yeah, kind of boggy, but okay. Good. Any other questions about that one? Okay. Oh, I'm skipping 3.3. It's on sampling from a small population, and we rarely need to do that. And so we need to move on with our lives. Sampling from small populations. We're going to skip it, which means our next section is 3.4, called random variables. Everything's random in this course, isn't it? I know, it's true, especially in this section. Probabilities, that kind of stuff. Okay, random variables. A random variable is a numeric quantity whose value depends on the outcome of a random event. Okay, to establish some basics here, we typically use a capital letter, capital X, for example, to denote a random variable. And then the values of a random variable are going to be denoted by a lowercase letter, usually the matching one, so a lowercase x. So for example, we're going to be able to say that the probability that a random variable equals the specific outcome. A common example is you roll a six-sided die, then this X, this capital X, is the roll of the die, and the probability that you roll a 1, for example, is some probability, 1 in 6, right? Six-sided, a fair six-sided die. And so now we're going to adjust those probabilities, or be able to adjust those probabilities, so they're not necessarily evenly distributed anymore, right? And so that's the benefit of establishing random variables. There are two types of random variables. We're going to focus on discrete random variables today. Okay. And so discrete random variables often take only integer values. Integers are whole numbers, right? And so I'll just make a note here. Whole numbers, right? Oops. So for example, your number of credit hours, the difference in the number of credit hours this term versus last, so it's some count, but in general, it's some whole number, right? And then a continuous random variable, which will sneak in at the end, because we're going to spend a lot of time on continuous random variables with the normal distribution in the next section. And so we'll just kind of introduce it today, hopefully, and then we'll work on it some more on Friday. But continuous random variables take decimal values, so real values. For example, the cost of books. We've got some decimals in there. The difference in the cost of the books this term versus last. So today we're going to focus on discrete random variables. So today, mostly. And we'll introduce continuous random variables, but we're often interested in the average outcome of a random variable. Now, the expected value is the mean or the average. It's been a while since we introduced those kind of same terms, but nice to have a reminder. So the expected value is the average, right? That's what you're expecting. That's your average outcome. Okay? And it's going to be a weighted average of the possible outcomes. Okay? How's this? Let's talk about how this is different from, recall, oops. X bar is the sample mean, right? On your formula sheet, the sample mean looks like this. It's the sum of the x's divided by n. This is going to be the expected value of x. If we introduce some new notation. But here, the problem is, this assumes that each x has a 1 over n probability, which is usually true, right? If we've randomly sampled, then by definition, everyone has a 1 in n probability of being selected, right? And so now this assumes the probability that x is equal to xi is 1 over n for all xi's. What does this look like? Let's do an example of some x's here. 4, 7, 11, and 10. If I asked you to find the average of these, right, just regular, assuming equal probabilities, find the average. X bar, what would you do? You would add them all up and divide by 4. 4 plus 7 plus 11 plus 10 divided by 4. Math says I can break up these fractions, right? And so this is going to be the same. I'm going to add a page here. This is going to be the same as 4 times 1 over 4 plus 7 times 1 over 4 plus 11 times 1 over 4 plus 10 times 1 over 4. That's legal math. Right? And so, right, if I have a fraction and I'm adding, then I can split that fraction as long as I do it for each of the terms. So that means that here, the probability that x equals xi is 1 over n, right? Or 1 over 4 in this case. I only have 4 things. So if I add that to my column here, and maybe what I'll do is recreate the magic down here. 4, 7, 11, 10. If we assume the probability that x equals xi is 1 over n, then each probability here would be 1/4, 1/4, 1/4, 1/4. We never have to think this much, but it's technically what we're doing. So if we map this back to this formula here, right, the expected value of x is the mean. And so what you're really doing is you're taking 4 times its probability of happening plus, right, because I'm summing over these, plus 7 times its probability of happening plus 11 times its probability of happening, right? And so what we can make is we can make a new column, sorry, xi times, and maybe I'll do xi here, times the probability that x equals xi. 4 times 1/4, oops, is 1. 7 times 1/4 is 1.75. 11 divided by 4, I'm cheating, 2.75, and 10 divided by 4 is 2.5. Right? Oh, you know what? Sorry, guys. I should show my work here. 4 times 1/4, 7 times 1/4, 11 times 1/4, and 10 times 1/4. If I add all these up, that's the same as the summation notation, right? So picking away at this summation up here, right? So far, we've calculated x times its probability for each of the terms. Now the last step is to add them all up, right? And so the result, if you add all these up, at the bottom here is the sum of your xi's times the probability that x equals xi, which in this case is 1 plus, whoops, not 11, 1.75. I get 8. Hopefully I did it right. What if we had just done this? What if I just asked you to find the average of these 4 numbers, right? You would have 4 plus 7 plus 11 plus 10 is 32 versus x bar is 4 plus 7 plus 11 plus 10 divided by 4 is 32 divided by 4, which is 8. Oh. That's a weird kind of gasping emoji face. This is easier, right? But it only works if we assume the same probability throughout, right? But there are many scenarios where we don't have the same probability associated with each outcome, right? And so, but we're gonna do this thing up here to find the weighted mean, it's called. Okay, so you assign a different weight to each value, and then you'll be able to find the mean. Okay? And so many outcomes do not have the same probability in those cases, we use the weighted mean. In those cases, we use the weighted mean. Which is just in general, the expected value of x is the sum of your xi's times the probability that x is equal to that xi. And this, look at us just blowing through this formula sheet. We're into discrete random variables. So here, that's what we're going to introduce today. The expected value in general is x times its probability. Add those all up, and then that's your mean. So here, that's this guy here. The variance looks scary, but it's not. Well, okay, maybe it is. But I'm not going to make you go too hard on it. So, as an example, what if we have these same values 4, 7, 11, 10? Just kind of 4, 7, 11, and 10. If these are all the possible outcomes, what's one of the things that I need to keep in mind? All my total probabilities have to add to 1, right? If I'm distributing all my probabilities across all the possible outcomes, they have to add to 1 still, right? And so here, the probability that x is equal to, xi, and I'll do an xi here, right? Where xi just represents, this is x1, this is x2, x3, x4, the xi is just a placeholder. So now, what if I say, okay, the probability of drawing a 4 is 0.25, right? We'll keep it at a quarter. Same rules apply for probabilities. All probabilities have to be between 0 and 1, right? And all the possible probabilities have to add to 1. Right? Then the probability of a 7, let's inflate that. Let's make it 0.6. You want to kind of keep track. I'm just making up these numbers. So what I want to keep track of is I need them to add to 1, right? And so here they kind of have to add to 1. So remaining, I have 0.6 plus 0.25, which is 0.85. So I have 0.15 to spread out over the rest. So I'll play it nice and safe and do 0.1 and 0.05. Just double check, 0.25 plus 0.6 plus 0.1 plus 0.05 gets me to 1. And so that's good. So now I have this unequal distribution or probability distribution. This is a probability distribution. If I want to find the expected value of x, then I take each of the x's and multiply it by its probability of happening. Right, the sum of your xi's times the probability that x equals xi. That's just from your formula sheet up here. Right? So now, what I like to do is I just like to make a new column next to my next to my probability distribution. Just find it's a nice way to organize my work. You don't have to, but I'm going to take the xi column and multiply it by the probability that x equals xi. 4 times 0.25 is 1. 7 times 0.6 is 4.2. I did it again. I should show my work. So sloppy. 11 times 0.10. 10 times 0.05. If I add these all up, right? So far I've done each of these components, right? For each of my observations, I've done x times the probability of that happening. Now I need to add those all up. One plus 4.2 plus 1.1 plus 0.5. I get 6.8. Does that make sense? I think so. Because 6.8, if the highest probability of one of these happening is 7, then I would expect my overall, my average outcome to be leaning towards 7. Right? The next highest outcome was 4, so that's why it's being pulled a little bit in that direction, right? It's being weighted more towards 4 and 7 than the other two, right? And so that's how you're going to find expected values or the means of uneven probability distributions. But like I showed you, it is what you're usually doing, but you would never go through all this work and split up the probability evenly and then multiply across and then add them all up when you can just add them up and divide by n, right? But technically it is what you're doing. So where does this come into play most often is card games or just kind of gambling in general. But any questions before we do an example? Okay. Oh, last thing I want to say here. Notice this is not one of the possible outcomes. This is if I repeated this experiment an infinite number of times, on average, I would expect 6.8 to be the outcome, right? And so here, notice 6.8 is not a possible outcome. But it is what I expect over many trials. Right, so on average, which there's definitely a note about kind of casinos and just gambling in general. But since we're looking at it here, there's an expected outcome. Okay? But we go in and we place it all on red or whatever, and we only do it once, right? And so there's some expected outcome. So, but the problem is, and so we can find those probabilities, but the casino itself gets to actually play an infinite number of trials, right? So they feel pretty confident in their expected payout, right? And so they're always going to set the price so that they're never going to have to have a negative expected payout, obviously. But the problem is they play an infinite number of times and we only go in and we play once or twice, or I don't know. Right. But a small number of times, and that's why the house always wins. Because otherwise they wouldn't have the house. The expected value of a discrete random variable. So like I said, a lot of the time, gambling or just kind of playing games and things like that. In a game of cards, you win $1 if you draw a heart. Okay. $5 if you draw an ace, including the ace of hearts. So that's kind of a special heart card. Okay. $10 if you draw the king of spades, and nothing for any other card that you draw. Write the probability model for your winnings and calculate your expected winning. So here, your expected winning. This is going to translate to the expected, we can call it W, or generically the expected value of X, but the X is going to be represented by how much you won, right? X is the amount of winnings. Which means that, let's start with that in our probability model. So write the probability model for your winnings. What that means, or what that's asking for, is this here, the probability distribution, and I should clarify, or model. I call it a probability distribution usually, I didn't catch that. But we can call it a model too, at which they have. So this section here is your probability model. So that's what we want to develop. So our X in this scenario is going to be our winnings, right? The amount of our winnings. They're going to have some probability of happening, right? Uh-oh, cards. It's okay. We're doing it together. Okay. But what you want to start with is, okay, X, all the possible winnings, right? Could be 1. And let's just make a note. You don't have to, but it does make it easier when we have to find the probabilities later. Okay. And so here, this is if you draw a heart card. You get $1. If you draw an ace, then you don't get the $1, you get $5. Or yeah, including the ace of hearts. Right? And so it would make a different model if the ace of hearts you got $6. But let's ignore that, right? They don't say that explicitly. So if you get an ace, then you get $5. If you draw a king of spades, that's specific. Specific because it's got a huge payout. $10. And everything else, you get nothing. All others, which is the complement, right? It's the complement of all these winning ones. You get $0. You don't want to forget about that option, right? Because that's the probability of drawing all the other ones is quite high, right? And so you need to put a weight of that probability onto that 0, right, in terms of your expectation. Now for the hard part, the probability that X is equal to this specific outcome, right, for each of these. What's the probability that you draw a heart card? It's one of the 4 suits, and there are 13 heart cards, right? 13 out of 52. So then the probability that's including the ace of hearts, right? But we should be putting the ace of hearts with the other group, right? And so now let's adjust this and say, okay, make it 12, right? Because the ace of hearts, to remove the ace of hearts, because the ace of hearts was a special case, right? And it pays out more. So then you want to put that probability on the 5 instead of the 1. So often it's good to kind of start with the basic probability and then think about, okay, are there any special circumstances that I want to remove, right? Just like this. But now my ace can be any of the 4 aces, right? Each suit has an ace. And so now this probability is 4 out of 52. There's only 1 king of spades, and there's no overlap with the other. Spades is a black card, and I don't know why I read hard and saw red, but that's weird. So no overlap. $10 with a probability of 1 in 52. Still a probability, but it's small. All the other ones. All the other cards, well, I'm taking from 52. I think the easiest way, instead of trying to identify which ones are all the others, how about if we did 52 and take away all the cards that I've already used, right? 52 minus 12 minus 4 minus 1 over 52 is what? 52 minus 12 minus 4 minus 1 is 35 over 52. Let me just see quickly if that makes a nice number. It does not. So these guys don't make nice numbers, and so I'm just going to keep them as fractions. And we can do a little bit of rounding. How rounded can we go? Probably shouldn't round more than 2 decimal places, because money is always to 2 decimal places. So if you're dealing with money, I would say keep at least 3 decimal places until the end, right? Ideally keep all of them, but for money, in the end, you're rounding to 2, so you want to keep more than 2 going through. Okay. So now, write the probability model for your winnings. That is, for your winnings. That's this. Then you're going to use it to calculate your expected winnings. Your expected winnings, right? Just in general, the expected value of x is the sum of your xi's times the probability that x equals xi. So you want to take this column, multiply it by its probability, and keep track, because then you're going to add those all up. I'll do an xi here. Xi times the probability of that xi happening is 1 times 12 over 52. 12, let's see if 12 over 52 is nice. Nope. 0.23077. I've rounded. Hmm. 5 times 4 over 52 . 0.384615. I don't know. I'm sure I'm keeping in a different number of decimal places. I'm just gonna go until there's no more interesting values. That kind of makes sense. I don't want to stop at the 1. I'd have to round it up to 2 and kind of make a mess. And so, but after 5, it trails off to 3, which then I lob it off. But like I said, if you just keep at least 3 decimal places in this case, then you're okay. 10 times 1 over 52. 10 divided by 52 is roughly 0.192307. Match it. 7. And then 0 times any probability is 0, 35 over 52. I add all these up. 0.2. I guess I should do it 0.23077. I'll do it with my rounded values. 0.384615 plus 0.192307 plus 0. I get the expected value of x is 0.8076927, or roughly 81 pennies. Right. Or $0.81. Right? Because it's the expected payout. And again, it's not one of the options, but if you played this game over and over and over and over and over again, then that's your expected payout. You can use that to decide how much to pay to play this game, right? What if it costs you $1 every time? That's no good. You're only expecting 81 cents per play. That's not necessarily what's going to happen. In fact, it's not one of the outcomes, right? But for each play, you're really only expecting an 81 cent return, right? And so then paying $1 each time, you would be running at a loss every single game, right? But if it only costs you 20 cents, sure, go ahead, play it, right? But like I said, usually the cost to play is more than the expected value. If we visualize the probability distribution, it would look something like this. And so again, notice 0.81 is not a possible outcome but it is the expected payout. Right, and that 0.81 is because we're weighting more toward the 0 and the 1 outcome, right? Kind of falls in here. And the probability of getting 0 payout is the highest. Right. There's variability, right? So there's some expected payout, but there's also going to be some variability in here, right? As we understand, right? You're not going to get a payout of 81 pennies, right? That's not one of the options. So there's going to be some variance here. Okay. And so we can calculate the variance, which it's been a while, but we use sigma squared, right? A lowercase sigma squared to denote the variance. Okay? And we can calculate the variance of x by, and there are kind of some familiar looking things in here. Okay? But the variance of x, it does rely on that same probability as before, right, from the expected value, but then it takes the expected value into account. So you first have to find the expected value, see how far is each of the payouts, for example, from the expected value, and then you square those, and then you multiply them by their probabilities, and then you add them all up. Just to finish talking about this blurb, sigma is the standard deviation of x. And so, which is still going to be the square root of the variance of x. In this case, we don't really use the square root of the sum of the x minus e of x squared times p of x squared. You just find the variance first and then take the square root. So here, find the variance of x first, then take the square root. I'm going to bring in, let's see if it's still, it is, nice. So here, the variance of x, this is the formula that's on this slide, right? Xi, how far is it from its expected value? Then you square it to get rid of any negatives, and then you multiply it by the probabilities, and then you add them all up. This is an alternative way of writing this formula that I don't use. So you can ignore this. I guess I shouldn't have put a line through it before I talked about it. I'll move the line though. If you prefer, yeah.
Can we mark these up and we'll get new ones on there?
Yeah, you'll have fresh ones on the test. Yeah, I encourage it, because then, with any luck in the test, you can kind of close your eyes and visualize your own markings. Right. Which is funny, but it kind of works, yeah. And you're always welcome to a fresh copy too, if you want. So here, if you want, you could use this formula instead. What would you have to do? You'd have to square each of the x's, right? Each of those winnings, 1 squared, 5 squared, 10 squared, 0 squared, multiply it by its corresponding probability, then subtract the expected value of x squared, okay, from each of these terms. Okay. I think it's actually more work than this previous one, but and then add them all up. But like I said, I'm gonna move this up here, bink, and you can ignore it. Maybe I should say if you want. You want to. Kind of an evil looking smiley face. It's appropriate. So the variance of x, just as a note, because I noticed on some of the assignment questions, they use kind of different notation, but as long as you remember that sigma squared is the variance and mu is the expected value of x, and then I'm guilty of it because then I use sigma. This lowercase x just means that it's a standard deviation of x. So this is just the standard deviation of x, which is the square root of the variance of x. Okay. So to find the variance, right, usually what I would recommend is building a table. In fact, on the test, I'm so nice and I give you the table, so you just need to know how to read it. You'll have some practice on the assignment, but you just need to be able to grab the appropriate information from a table that looks like this. And maybe, just maybe, we'll build it out together first. So to calculate the variance of x, which is the sum of, whoop, disappeared. The sum of each of the xi's minus the expected value of x, then square it times the probability of x equals xi from a probability distribution. Let's bump this down here. From a probability distribution or model. That probability distribution looks like this. Xi, let's say x1, x2, x3, x4. We just have 4 things for now. Each has a probability that x equals xi. Or should we do the winnings? It's on the next slide, but we can do it. Sorry. Let's do that instead. Not just the generic x. We got 1, we got 5, we got 10, or we got 0. With some probabilities that I'm going to steal from, I never wrote them out. Oh, set myself up. 12 over 52, 4 over 52, 1 over 52, and what was the remaining? 35 over 52? So this is this. So you'll be given that. First thing you need to find is the expected value of x, which we know from practice looks like what? So kind of the first thing you need to do is find e of x. can I do this instead? I'll label it 1 and then 1 down here. Find E of x. E of x is the sum of your xi's times the probability that x equals xi, which means you need to make a new column with xi times the probability of xi. Xi times the probability of x equals xi. And I'm gonna need just a little bit more room. Scooch it all the way over. Okay. We already did this, but did I write it out properly? Stealable. Hopefully. Sort of. I'll redistribute here. In fact, put this down, just even it out a little bit. I stole that from earlier. Now, instead of it saying E of x down here, it would say the sum of all these. I would give you the sum of all these. In fact, I might give it to you even for the probabilities, but they have to add to 1, right? So that's kind of boring. But we know that this is the expected value of x. Let's use a rounded value. In this case, the expected value of x, let's use 0.81, right? Because it's money, right? And so then it makes more sense to just keep it at 2 decimal places. Okay. You want to kind of find the inside of your onion and then work your way out nice and slow. And so we started here at the expected value of x. The next thing you want to do is find each value of x. How far is it from the expected value of x? Some will be above and some will be below, right? And so now we need to make a new column where 2 is calculate xi minus the expected value of x for each x. So here, xi minus the expected value of x, but the expected value of x is 0.81 for each of these, right? And so now I look back here and I have 1 minus 0.81. 1 minus 0.81 is 0.19. 5 minus 0.81 4.19. 10 minus 0.81 9.19. And then 0 minus 0.81 negative 0.81. Right? So how far is each of these from the mean? Right? That's familiar. Right? That's the deviation from the mean. And then we have to square it so that we're not adding negatives. Yeah? Because they'll cancel, and that's not how the spread works. Right? Just because you're below the mean doesn't mean that that you get to cancel the spread. That's part of the spread. Right? And so that leads us to the next part where we take each of the values we just found and we have to square them. Right? So now, what color can I use here? How about purple? Square each deviation. So here, got a ways to go. So that's why I need to kind of scooch it over. Bless you. So now I take xi minus the expected value of x and I square it, putting me at 0.19 squared. 0.19 squared is 0.0361. 4.19 squared is 17.5561. 9.19 squared $84.4561, and negative 0.81. If you get a negative result, you want to be careful because negative squared become positive. That's the whole point. And so you want to be careful because a lot of calculators, if you don't use brackets around your negative number, it'll just put the negative outside. That's what you want to be careful of. Or I usually cheat and I don't even write the negative because I know it's going to be positive anyways. The decoy here is I could add all these up, but they're not useful to me. We don't need them for our formulas, so that's why I haven't been doing it. I could add all these up, but again, not useful to me, so I haven't been doing it. But in the table that I give you, it would give you the sum of the xi's minus the expected value of x squared. And below here, it would give you the sum of your xi's minus the expected value of x. But like I said, it's your job to know that you don't need those. Right? What do you need? We're so close. You need to take all of those squared deviations that we found and multiply it by its respective probability, and then add those all up. Right? And so here I'll use pink for my grand finale. Maybe it's too similar to purple. Sorry, guys. And how am I going to squeeze it on? Oh, well, I'll try. 4, multiply each squared deviation by its respective probability. The sum will be the variance. That's way too lofty over here. Uh-oh. How can I fix it? That should be enough room. Oof. Oh. Scooch those over. There. I did it. I recovered. Because I had to make room for that one last column, which is the previous column times its probability, or if you prefer, if you're feeling comfortable with it, because the probability appears first in the table, you might want to do the probability times the last column. Doesn't matter. A times B is the same as B times A, so order doesn't matter there. And so I'm going to write it to match the formula. So you have xi minus the expected value of x, square it times the probability of each of these things. Okay. Do I have room? Point 0361 times 12 over 52. 0.0361 divided by, or times 12 over 52. It's going to be very small. 0.008331. And I know what you're thinking. Wow, this would be so much easier if I could just use Excel, right? And you can just reference the cells, do it for one, drag it down, right? Here, and that would keep all your decimal places, right? That's nice. 17.5561 times 4 over 52. 1.3505. Do some nasty rounding there. 84.4561 times 1 over 52. 1.62416. And finally, 0.6561 times 35 over 52. 0.4416. Good measure. Adding all these up will get me to the variance. Right? And so let's see here. 0.008331 plus 1.3505 plus 1.62416 plus 0.44161. I get 3.42461. Therefore, the variance of x, which is the sum of each of the xi's minus the expected value of x squared times the probability of each of those xi's, is 3.42461. Whoo! Quite a large spread around my expected payout of 81 pennies. And What's the standard deviation of X? Find the standard deviation of the payout. We said the standard deviation of X is going to be the square root of the variance of X, which is going to be the square root of 3.424601. Get 1.850567751. Again, because it's money, you can round it to 2 decimal places, but I'll just leave it there. And like I said, we've got kind of bigger fish to fry in chapter 4 before the test. And so for this on our first test, I will give you a table that looks like this with all the sums at the bottom, right? And then I'll ask you, hey, what's the expected payout, for example? And then what's the variance of the payout? What's the standard deviation of the payout? So you don't need to generate this. You do in an assignment question, I'm pretty sure. But you won't need to generate it. You need to be able to read it and pull out the information. Because like I said, usually we would just use Excel anyways. So you wouldn't need to do it by hand. But here it is. Any questions about that? Nice. I really hope that they found the same thing we did. Looks similar. Is it the 0.44? Oh, phew. Okay. They did some other rounding, but that's okay. Quick note on linear combinations. A linear combination of random variables x and y. So I can combine 2 random variables. That would be something like if I roll a 6-sided die and then I follow it up with drawing a card from a deck of cards, for example. So I'm combining 2 random variables. For example, if X is roll a die and maybe Y is draw a card or something like that, just kind of combining 2 things. Then maybe I roll the die 4 times and I only draw a card 2 times or something like that. Then we can write out this linear combination as ax plus by. Now, that's not something that we're going to do, but I do want to highlight that the average value of this linear combination is it distributes. And so the expected value distributes. And I don't like how they wrote this. So I'm going to rewrite it and maybe down below. What do I not like about it? I don't like that they use the multiplier x in general. That's kind of bad math form, right? And so unless it's really obvious, but here we're using x's, and so incorporating an x as a multiplier is kind of bad. Oh, ax plus by. What happens is a is just some number, and so the expected value of that number is just itself, right? It can only be 4, right? And so then you would say, well, then I'm expecting 4 to be 4 always. And so you can kind of bypass it and say, okay, well, this expected value is going to latch onto these variables that have random outcomes. So what this looks like is you get A times the expected value of X plus B times the expected value of Y. For example, any questions about that one before we do this example? On average, you take 10 minutes for each statistics homework problem and 15 minutes for each chemistry homework problem. This week, you have 5 stats problems and 4 chemistry problems assigned. What's the total time you expect to spend on statistics and physics? Haha, nice try, guys. Let's say chemistry. I don't know if that's on purpose. Did I keep the, or if it's a typo? Let's do chemistry just for simplicity. Right. So then we're given that the expected time for a statistics problem is 10 minutes. Right. That's the expected time. You understand that some are shorter, some are longer, right? But on average, you're expecting it to take about 10 minutes. And the expected time for a chemistry problem is 15 minutes. Now you're sitting there and you're doing homework and you've got 5 statistics problems and 4 chemistry problems. And you want to find how long is this expected to take. Now I know that, okay, the expected value of 5 is 5 because I don't expect it to change, but the expected value of S we know is 10 minutes. So this becomes 5 times the expected value of S plus 4 times the expected value of C. Which is 5 times 10 plus 4 times 15. 50 plus 60. 110 minutes. Or almost 2 hours. You could have answered this problem without knowing expected values, right? If you just kind of ignored everything that we had just talked about, you could still calculate this, right? So really what we're doing is we're just showing that there is kind of more to it than what you're doing, right? But you know how to solve these problems. And so, but it's kind of nice to attach some formal notation and formal theory to it. Or maybe it's not nice, I don't know. But just remember, you know how to solve these, right? The expected value behaves the way you want it to. The variance, not so much. So the variability, so the variance of a linear combination of 2 independent random outcomes looks like this. So same thing, I'm going to rewrite this. What happens is, or the var if you prefer, kind of inconsistent notation here. But what happens when you bump this A outside is it squares. And that's because the variance is a squared unit thing. And so now, as long as you know the variance of X and the variance of Y, then you can still look at a linear combination AX plus BY, as long as you remember that you have to square those coefficients. And then I'll just highlight that it's for two independent random variables. We're not gonna consider not independent. But then to find the standard deviation, you have to find the variance first and then take the square root. Need to find the variance of ax plus by first, then take the square root. Right, because the square root of a linear combination doesn't work the same, the way you want it to. So here, just as a little note, if the random variables are not independent, then it kind of takes its own form and we're not going to deal with that. I know, I'm out of time. Luckily, I already cut this one because I don't like it. Because it goes against what I just told you. Okay. I know, I'm all out of time. Can I do this? Try on your own. It's another one. Before I post the notes, I'll bring the solutions to this one into the notes, right? Just so you can check it. But we are starting the normal distribution next week. And so that's why I'm kind of rushing through this. But, oh yeah, Vegas, blah, blah, blah. Just as a quick note here, the expected value behaves the way you want it to, but the variance does not. And that's it. I know. But like I said, all I'm expecting you to do is read that table that we generated for this stuff. If you have any questions, let me know. Otherwise, I'll see you on Friday.